Hello everyone, and yes, I have my friend here with me, going to do mathematics today, my seal. And today we're going into our second preliminary, which is something called differentials, as we're on this journey to prove the chain rule. So let's hop on the drawing pad and animation and let's get going.
Differentials. Well, what about differentials? Well, in this video we're going to make the connection between the quantities dy and dx. We'll treat them sort of as variables, which will then add meaning to Leibniz's derivative notation, dy by dx. Now you may be wondering what exactly are differentials and how do they work and interact? Well, they interact by this following notation. dy is equal to f prime of x, the derivative, times dx. Sometimes we write a delta x over here, but we'll replace that with dx, and we'll stick to this notation. What happens if we consider this dx as sort of a number or a variable and we formally divide both sides? May seem extreme, but we formally divide both sides. We would get the following expression, dy by dx, Leibniz's derivative notation. And so this differential notation adds more meaning to Leibniz's derivative notation in that it's sort of could be thought of as a ratio of differentials, a ratio of two small changes, a ratio of infinitesimals, just like how Leibniz thought of it, which adds more meaning to this notation. Now, dy in this notation is what we call the differential of y, while dx is what we call the differential of x, and dy and dx just represent small changes in something. Now I'll show you graphically what it means in a bit more detail.
Alright, so notice here we have a differentiable curve, the blue curve, and we have a tangent line at a point x naught. And that tangent line, as we've seen in the previous video, is also considered a linear approximation to the curve. Alright, and we have another point separated by dx, a change in x. So we have x naught plus dx, another point, with its coordinates. And then we notice here that the linearization changes by delta L. We notice that the linearization changes by delta L. For a change in x, there's a change in this linearization over here. And we have the actual change of the function, which is much greater than the change in the linearization, which is represented by this here, delta f, this whole part over here. And the goal here is to kind of estimate the change of the function using its linear approximation, delta L, and we'll find sort of expressions for this. Now, let's go back to the differential. So the differential says dy is equal to f prime of x, the derivative, times dx. First thing we're doing here is that rather than writing delta y or delta f, the change in the function, we are writing dy. And rather than writing delta x, it's going to be equal to dx. So these are the replacements we're making. And now what does this differential tell us? Well, it tells us dy, a change in the function, is going to be f prime times dx. Alright, so what can we say about dy by dx? Okay, now if we take the linearization, it's a tangent line. And we separated 2 points by dx and it gave us a change. And that's supposed to give us a change, dy, a change in this linear function. So what we could say is dy by dx is equal to f prime of x to get the differential expression, which is the change in our linearization, this linear line. And that is why we wrote delta L as f prime of x times dx. Now, given that graph, let's work things out. And I've written here to the side what we've learned from last video, the formula for a linear approximation as we see on the graph. Alright, and we're going to focus on this linear approximation and its change, delta L, which we defined as f prime of x dx. We got it by knowing that the slope of the linearization, which is the derivative of the curve, is just dy by dx and is equal to f prime of x, and we've formally multiplied treating dx as a number. Now let's focus on what's happening to the linearization. Well, the linearization essentially is just a function, as we've seen in our previous video and as represented by the formula on the side. It's just a function. So we could write delta L is equal to L of x naught plus dx, the separation between the 2 points. Alright, minus L of x naught. And let's rewrite this, considering this as an input to the function which is defined by the following equation that I've written down on this side, and as we've deduced in the previous video. So we will plug in f of a, any point we're considering for the linear approximation. In this case, it's x naught. So we'll write f of x naught, the point at which there's a linear approximation, plus the derivative at that point, times x plus dx, this arbitrary point, or sort of the x value that we're inputting here, if you see on the side, minus the point we're considering. All right, so sort of a general equation. All right, so sort of a general equation, minus, we just plug in now L of x naught. We would get f of x naught. You can find that just by plugging in for yourself. All right, now let's simplify. F of x naught goes with the other f of x naught. F prime of x naught plus dx minus x naught. Well, this x naught over here cancels with the other one. There's 0, and so we end up with f prime of x naught times just this dx. What's remaining? These two. And so we can write finally that delta L is equal to f prime of x times dx, which, as we said in the beginning, is true. So we found it's true. And we've also found that the differential actually has a geometric representation, a geometric meaning. How? Well, if we look back to our curve, we see that the differentiable curve, okay, and its linear approximation is over here. The curve changes corresponding to a change in x, and the linear approximation changes corresponding to the same change in x, but smaller. So here's the change in y, all this, change in y or change in f, and here's the change in the linear approximation, delta L. And what we could say about all this is that the delta L is equal to f prime of x dx. Using the derivative of the function and a change in x, we could find an estimate to the change in f. So that's why we say delta y is equal to dy in the differential, which is equal to delta L. So delta L is equal to dy, which is what we call the estimate or the approximate change of the true change in f. So this is the actual change, this whole big thing, while the change in the linearization, or dy as we defined it, is an estimate because it's smaller. It's an approximation to the change in the function. So I hope you've understood that differentials have a geometric representation and they extend the definition of Leibniz's notation of a derivative. See you in the next one. Thank you. Looking between the two. Yeah. See you in the next one.